Hi, everyone. Thanks so much for joining us today. We're going to give it a few more moments for people to log on, and then we'll go ahead and get started. Thank you. Hi, everyone. Thank you so much for joining us for Microsoft's continued investments in the UEFI ecosystem, part of the UEFI 2020 Virtual Plug Fest. We want to take a moment here to introduce you to the presenters of this webinar. The first one is Jeremiah Cox, who's a senior software engineer at Microsoft.
Good morning. Good to be here.
We also have Brett Barkaloo, who is part of the Microsoft security team as well, Firmware team.
That's not my title. Hi, good morning.
And then we have Matthew Carlson, who is a software engineer at Microsoft.
Hey.
I'll pass it off to them.
All right, sounds good. Thank you, Megan. I think we're all still waking up this morning, so apologies if there's a preponderance of us and ahs. But we were excited to take this opportunity to speak to everybody. I think we joined everybody in frustrations around the cancellation of PlugFest. That said, as per usual, our talk is somewhat loosely organized. This time around, rather than doing a specific technology or a deep dive, we really kind of wanted to put together a retrospective of what we've done over the last year, with a focus on how that relates to UEFI, how that speaks to our view of the role of UEFI, and what role that is going to take going forwards with our future contributions and sort of what we see for the ecosystem. So I wanted to start by acknowledging something that I've heard with increased frequency. I've been in several meetings and at several board tables where somebody has brought up that UEFI is too blank, and you can fill in the blank. It's, UEFI is too big, UEFI is too slow, it's too inflexible. Why would we use a UEFI-based solution when we're trying to design X and we know what X needs to be, and we just boot? And this is particularly prevalent in the embedded ecosystem, where things have come out of sort of a U-boot or core boot background. They're used to, just set the system up, make RAM available, jump directly into a kernel. Why do we need to get any more complicated than that? But in reality, the devices, especially the devices in the embedded space, have been growing at just an incredible rate towards being more robust, more powerful. They're interacting together. They need recovery stories. They need rapid update stories. And at the end of the day, they're needing the same, they're trying to solve the same problems that UEFI was invented to solve. They're approaching the same problems that the PC ecosystem had to address years ago. And that's really the places that we think that UEFI continues to excel. So that's kind of a long-winded way of saying that even though there are other alternatives and certainly plenty of opportunities to say, well, what about the pros and cons of this solution over UEFI, we still think that in almost all spaces, UEFI is a superior solution. The design philosophy, the ideas of componentization, the ideas of specification of how those components are to interact, the ideas of going into a process with the goal of writing a specification, even if that specification does need revision down the line, but agreeing on interfaces between not just the firmware and the OS, but the firmware and other components of the firmware are problems that continue, or the solutions to those problems continue to pay dividends in many aspects of the ecosystem. Not only that, but it's coming from, like I said, a PC background where these are established players who have seen the problems and have done their best to address the problems. And time again, when we see these when we see these questions come up in meetings involving other technologies, our response is, well, if we were doing it with UEFI, that would already be addressed. Part of the size and part of the complexity of UEFI is because it is addressing a lot of these issues. And to acknowledge the criticisms that are leveled against UEFI about it being, perhaps a little larger than some people want to take on, or perhaps a little bit more difficult to make changes to. It's not as nimble as some more agile workflows. We think that the work over the last year to establish processes around a code-first implementation of, or a code-first process of, let's design a component, let's describe a problem statement, and then let's take a stab at actually putting that solution into a system and see where the rough edges are and where the problems emerge around implementation. I think we think that is going to go a long way to addressing these nimbleness issues, because by solving the problem right or in an implementable way the first time, we don't have to pivot as many times and we don't have to spend as much time in the specification. So that's going to be kind of an overall theme of the next couple of sections. So thanks for joining for that. And I'll hand off to Matt, who's going to talk about some of our open source contributions.
Thanks, Brett. Hi, this is Matt Carlson here. Yeah, we just kind of wanted to do a brief purview of kind of some of the things that we've done recently and contributed to the community that has kind of followed this idea of trying something out, seeing what happens, refining it, polishing it, and then working towards an eventual spec or model. One of the first things was something we refer to as pie tools. It's a common joke that everyone seems to come up with their own form of build system, whether that's just a simple batch or shell script, or something complicated and big and extensible, and we're no exception to that rule. We had this small system that sort of was simple and included inside of every platform, but then it sort of grew and became slightly more complicated, and it was a little bit more generic. The focus on this was on dependency management and making sure that builds were very deterministic and reproducible. And that's kind of how it got started. It was just this little chunk of our code base, and it grew into something more and more. And we kind of realized, hey, this might be something. So we said, after 3 or 4 iterations, including some complete rewrites, we said, you know what? Maybe there's something to this. And it was when we really started to focus on incorporating continuous integration, or CI, that we thought, you know what, we should share and help others build their CI story. Maybe this isn't the final solution, but we know as a community we've talked about having some sort of CI system and saying, okay, we should not check in code that is broken, but we should also have checks to make sure that we're not checking in code that's broken. And so we worked with the community and added a few different repositories, and they're kind of broken up into 3 sections. There is Python library, which is basically firmware-specific Python code. Has things like parsers and loggers and capsule data management and a few other things, whereas there's this other side of it called extensions, which is more EDK2 specific, more command line focus, and then within extensions there's this small little circle called Steward, and that is the actual running things like there's setup, which manages your submodules, and there's update, which will fetch external web dependencies and NuGet dependencies, and then there's CI and build, which builds CI or platforms. And it's called Stewart mostly because a coworker and I thought it'd be really funny, and it is. So, as I mentioned before, PyTools was really meant to sort of an experiment. It was an example of how things could be. It has a full GitHub process with PRs and issues and milestones. It has this idea that it's very, very extensible. Has this idea of an invocable that anyone can write their own if they want to create a different sort of way of doing things that we haven't even thought of. It should be easier. The goal is to make people's life easier, and this is actually proving to be a model for other firmware-specific Python repos that are being created they're following this idea and a general process that was established in PyTools. And as I mentioned before, one of the big reasons we pushed this out to the community was, in fact, the CI and unit test system. And it basically leverages these for just a really cohesive, fantastic drop-in experience. Like I mentioned, there's a plugin model that is very, very flexible and very extensible. So, for example, some tests that I've written have been, compiling tests, host-based unit tests, DSC completeness checks, which basically just says, okay, are all the libraries in this particular package in the DSC to make sure that they are, in fact, being built and tested when you check into your code. And with that, I would like to turn the time over to Jeremiah to talk about some of our other implementation-first initiatives.
Thank you, Matt. So before I dive in, I wanted to give a little historical context and explain, share why we're trying out this implementation-first thing. So I've had the pleasure over the years to lead many of Microsoft's spec-first initiatives, and most of the, predominantly all of the small ones were successful. The largest, most complex, I'd say, success was Secure Boot almost a decade ago. Though appearing spec first, I would share that it was actually informed by more than 3 proof of concept implementations from different vendors. So we did sort of iterate internally, and you'll notice that when we did ship Secure Boot way back, we landed on version 2.3.1 errata C. That was the Windows logo requirement. So there was some iteration before we actually shipped Windows 8 with this feature working in the ecosystem. And then funny story, Secure Boot was also where we had a lesson learned. Later, I believe it was spec 2.5, we augmented Secure Boot with something called deployed mode to try to solve sort of the lessons that we had learned in those first years of Secure Boot. However, after spending lots of time on the chalkboard, chatting together, writing up the spec, iterating, and then publishing the spec, when we went to go out and attempt to deploy this in the ecosystem, we found that there were several blockers that just prevented it from actually working. And so this was sort of a learning that we took and said, maybe we should, for these big features in particular, try to implement them first and vet them sort of end to end to make sure that those critical pieces actually would work end to end. And so we'll give some examples of that. Now, also implementing first gives us some experimentation room, which lets us really evaluate the cost-benefit trade-offs before we actually try to bring something to market. Okay. So first I'll talk about DFCI, the Device Firmware Configuration Interface. In a nutshell, this is bringing the security features that you would have in a BIOS menu to the cloud. So instead of having to physically touch a machine, enter a BIOS menu, toggle these things, now you can go to a cloud interface. This is Microsoft Intune and Azure, and configure these settings, and they'll be securely pushed to your device. There's a lot of things going on here that make this a complex feature. Obviously security, but also usability, recovery stories. When you have settings that might prevent a machine from booting, you better have a good recovery story. You really don't want to have to open the case and attach a flash programmer to recover a device. That's unacceptable. So getting all those features in place, the web services working end to end, was a really large lift, and we've implemented that and have open source code actually available now. The feature is actually still in public preview. Oops. That's why we're still polishing out some edges while we have folks start integrating the code, so that we'll feel better when this goes general availability. All right. Another example, we stuck with the firmware configuration interfaces. This is MFCI. This one is an example of how there was a feature that some OEMs had. This is about being able to sort of securely enable a non-retail device mode on a device that's already shipped and been secured. So there's some security sensitive settings, perhaps related to calibration, safety, compliance, that you generally wouldn't want malware to be able to tamper with in the field, and so you would secure those before a device leaves the factory. This provides a secure way to sort of unlock and allow the OEM or customer service center to adjust those settings, again, in a safe and secure manner. So when we looked at this, we found that there were maybe a few blockers to more broader adoption. We really wanted to scale this awesome capability out to all OEMs. And a couple things perhaps preventing adoption. One, there is no open source reference available. And two, and perhaps the bigger one again, is having actually secure signing services that were available at a cost-effective price point. Right, those things are not easy. That was one of the things that we solved in DFCI, and here in MFCI we're doing the same thing, where we'll be making these services available to OEMs so that they can build this end-to-end secure unlock story. So again, right, we're actually still in the process of building this. So the code that is available is in beta. Expect it to churn. So look at it, give us feedback, but be aware that there may be some changes as we continue to complete the bringing up the service and integrating this end to end and test it and make it production ready. And with that, I will turn over to Brett again to talk about variable policy.
Thanks, Jeremiah. Yeah, I think it's important to open every single handoff with that. So variable policy, if you've participated in any of the EDK2 dev talks, this is something that we've been talking about for over a year now. It arose, it's very likely that it could have stayed entirely in the EDK2 community because it kind of grew out of a very implementation-targeted feature. It grew out of variable lock and then a related technology or a related interface called variable property, which was heavily tied to the way that EDK2 and TianoCore implemented their variable services. It was not generic to variable services. It was this other thing that if you knew which SMIs to trigger and which parameters to pass, it would enable you to do that. And it was an interface that was also shut down at a certain point that would not have been exposable to any other components. What we discovered was that this, we started by asking, well, can we enable the optional implementation of variable lock? We want a variable lock that the code could submit the lock at one point, but it doesn't necessarily go into effect until a later point. The problem statement here was we had chunks of code that understood policy and that wanted to establish policy, and we had other chunks of code that just needed to interact with resources. And the code that controlled policy we wanted to execute in a deterministic way. Whether or not those resources were ever touched, whether or not those components ever loaded, we still wanted assurances that these events were going to complete and that the policy would be enforced. Where this took a sharp left turn was when we started working on architectures that had alternate implementations of variable services. All of a sudden the SMI with just the known parameters, in order to continue using that, we'd have to describe an interface around it, and then that interface would be tied to an SMI-based implementation, and we didn't want that because we were investigating solutions such as off-chip policy enforcement, off-SOC variable store, or off-SPI variable store, and there was very likely that there'd be some other entity that would need to know about it. And this is exactly the problem statement that a lot of the UEFI specifications were designed for, is that by describing an interface that can be interacted through using runtime services, you now have this standard approach that whether you're doing it on SOC or on SPI or in some other component, the communication interface would remain the same. So we started writing it up that way. And the code that is available in Mu and is actually about to land in TianoCore is taking that approach of even if you weren't using a TianoCore implementation, you could use this interface to interact with somebody who has implemented variable policy. So the loop kind of closed nicely on that one, and that is one thing that we've contributed. Another thing that we were actively working on is called PRM. And PRM is a proposal on how to address some of the difficulties with, sort of the realities of a system that's running a host OS, but there are still runtime events that happen through SMM, and a combination of SMM being very expensive for certain operations, and also the host OS increasingly needing to know which SMM events are occurring, and at least, even if they don't have any control over it, at least having some understanding of what's about to happen has come up as a topic that's really important, both from security and from a performance perspective on servers. And so this is an ongoing effort to establish an interface by which the process, a particular handler, could be removed from SMM. It could retain all of the advantages of being executable no matter what your OS environment is. Where everybody that's involved in this conversation is very conscious of the fact that one of the attractive reasons of writing something for SMM is not only do you know for a fact that it stays resident, but you know that I only have to write this routine once. I don't have to package it up as a driver for different flavors of a kernel or for different OSs entirely. I know that I can write it once, and whatever code I leave with the machine will be able to execute. So while trying to maintain that advantage, PRM says, well, we could componentize this and establish a standard calling interface and expose that calling interface through ACPI. So rather than just blindly triggering an SMM with the correct values and hoping that there's a handler on the other end to deal with it, the OS would be able to identify, or an ACPI event could trigger that this is something that, this is a routine that the OS should stop and dispatch. By moving this into the OS, as I mentioned, you get the performance advantage of now you can run it on a single thread, potentially, or a single core, rather than having to pay the cost of rendezvousing all of the cores to wait for the process to be handled in SMM, which has significant advantages on, massively multi-core systems. By nature of it being in development, we wanted to get some of our early work and our early ideas out as quickly as possible, because if you have a problem with this approach, if you see difficulties that we're not seeing that aren't part of the conversation, we are eager to get as many viewpoints as possible, because the ultimate goal of this is, in order for it to be successful, it's going to have to land in the UEFI spec, because it's going to have to be something that all operating systems know how to interact with. So yeah, that's one that we're really excited to work with everybody on. I think there used to be a divider slide here, and it didn't make it into this version of the deck, but I'll go ahead and say that in that way of establishing interfaces for operating systems and other components to consume, one of the things that we've worked on a lot over the past year is a binary model for certain components. There are a number of solutions that are being discussed right now. I think Intel has a proposal out. We've published prior work around the concept of FVIS, which is a firmware volume of independently serviceable drivers that we're revisiting now with the active discussion around other binary models. But something that Matthew has had particular experience with over the last year, and especially over the last 6 months, is can we put a binary model around crypto? And this has a bunch of advantages and also a bunch of challenges that I'll let him go into.
Thanks, Brett. As Brett alluded to, the binary model is just packing a driver or some other source into binary form, so pre-compiling it, and then including it in a platform. The key here is making sure that you have a verifiable source and that you know where it's coming from. The reason you would do this would be to improve developer productivity and to improve serviceability, FVIS being one solution. Having all your code instead of statically linked throughout your firmware volume, having it in just one spot makes it really easy to update. As Brett mentioned, one of the first things we decided, we said, okay, there's all these proposals for this binary model. We think that there's a lot of advantages here. There's been some, some RFCs and some kind of iterating on thought. Let's just see where we can get. And this was our first attempt at a binary model. It went through dozens, if not more, iterations. You might say it's really easy. You take the library interface, you convert it into a protocol interface, you precompile it, you build a wrapper library that just calls into that new protocol, bam, you're done. And in one sense, yeah, that is exactly what we did. However, we realized that things like libraries being linked in, especially non-platform specific libraries, since it needs to work across all platforms, as well as some other challenges such as binary alignment and other things, made this a little trickier than we initially thought. However, we did make it into EDK2 on February 7th, 2020. So far in most developer platforms, we see about 100 to 200 kilobytes of Dixie savings, and that's after compression. And usually about 3 to 5 minutes of build time per build saved. And as we mentioned, we talk about our CI system a lot. That includes CI for platforms. And this is thousands of hours and, you know, a significant amount of money and server time saved every year. So we've seen some pretty good advantages here. Okay, there's not a slide there. Anyway, one of the things we kind of talked about is where do you store this binary? Is it on GitHub? Is it a file mirror? Is it in the email archive? Is it a NuGet package? Is it a Azure DevOps artifact? And that is one thing that we've kind of iterated on and tried a few different things to see what we like and what we didn't, so that way we could better propose here are what we think works best, and here are other things that people are welcome to try and maybe it work better for them. But at least we kind of have those lessons learned. In general, the lessons that I think we took away from this was that every platform is different. They can be supported if you plan on it, and proving the versioning and the source that it was built from is very important. Having a chain of trust, particularly with security patches. Independent serviceability, our dream of being able to swap out crypto, as it's one of the components that likely will need to be updated the most. You know, if there's a security revision in OpenSSL or another crypto underlying library that you use, that's what you're going to want to swap. And when you have this new blob of firmware code for a specific section in your flash, how do you verify that it's a good section, that it's signed, that it's coming from, you know, a good source when that particular section of the flash has crypto on it? So how do you verify crypto without using crypto? So that is still something we're working on, and challenges that I don't think we would have foreseen if we had just written a spec. Looking forward, we're really excited about this model and excited to kind of work towards specification, if that's a word. This will include improving the transparency of binaries, improving the ease of integration into platforms, as well as allowing the community to work towards binitarizing more components. I will say another lesson learned, I just remembered looking at my notes, is it is crucial to make sure that the source of what you are building is open source, that people can look at, that you're not just handing them, here's this blob, trust me. And that's what I was kind of alluding to with the source and the versioning being crucial. Next, I'd like to hand over the time to Brett to kind of talk about our takeaways.
Sure. And
did you want this?
I don't know. Take it.
All right.
I think you had the more notes on this.
Right. All right. So thank you, Brett. Thank you, Matt. All right. So hopefully we've, you know, through showing you our PyTools, CI, unit testing, as well as, you know, our continued open source reference code that we're broadening the open source feature set, as well as providing, you know, Microsoft services to back some of these features, that we're really improving the experience of developing UEFI code, making folks more efficient so they can focus their time on the hard work of servicing and maintaining products and building, you know, awesome new products. Let's, you know, help all of us focus on the real problems. You know, we're producing more of these sort of end-to-end tested pieces of code as open source that we're hoping are easier to consume, and then once you've consumed them, they actually get used, not dead-end things. And then, yeah, again, just broadening that open source feature set so that folks can more easily adopt you know, some of these technologies. And that is, I believe, what we have for today. So now we can open it up for questions.
Great, thank you. The first question, it looks like Microsoft is continuing to invest heavily in UEFI. Can you speak more to your UEFI plans moving forward?
And I think I'll say that we're going to continue investing both on in improving the developer experience, in open source implementations. We believe we found some success here, and then obviously where it makes sense, we're happy to then collaborate on the specification, but really we're finding good success in this implementation first model, we think. And continue down that path. I don't know, Brett, anyone want to add to that?
No, that's pretty much it. Sorry, I had a bit of a blank. No, I think yeah, what we've talked about so far is largely the direction we're heading in.
Next question, what do you consider a host-based unit test?
Fantastic question. So for the host-based unit tests, we are largely, wow, the lack of sleep really has caught up with me. Sorry. The host-based unit tests are tests that run on a host rather than a target. Not to be cynical in my answer, but the idea being that similar to some other C-based frameworks, instead of building a large payload, so a large ROM, and then putting it on a target system, or even if you're not building a ROM, instead of building a module or an application to run as an EFI, what you're actually doing is you're building portions of that business logic into an executable that runs on your dev system in reality. So whatever your build system is will run this executable. It'll be built to a native binary for that platform. And the test cases will dispatch not so much to evaluate how the hardware reacts. So this is not a good place to test register configuration or run the race conditions or anything that is hardware specific, but it's a fantastic environment to test to make sure, did I cover all of my possible parameters that are being passed into this routine, or did I make sure to account for freeing this memory? By the time I make it out of this routine, any buffers that were allocated internally should be freed, that no null pointers should be consumed. It also provides you a platform to do more robust fuzzing, because you can, once you've abstracted the interfaces to the point where you can run these unit tests, you can also just randomize those inputs and fuzz them. So one of the advantages of this is not only the simplicity of being able to run an executable, but you gain a lot of speed, and you also gain a flexibility of environment. So by having a host-based unit test for as many things as possible, we can run those tests on the build server or as part of a PR gate to make sure that these interfaces are upheld.
And if I might comment, I'm pretty sure that host-based unit test endeavor was actually a collaboration with our fine friends over at Intel, right, Brett?
Yeah, I think it definitely came from some of the ideas that were developed in HBFA. This is, I think, for the last 3 or 4 Plug Fests, this has been a sidebar discussion of many of the people in the room to say, how do we improve this testing story? And this is one of the things to come out of that.
Awesome. Hopefully
we got binary.
Go ahead.
Sorry. Does the binary model need to be reproducible build tool chain, e.g. exactly same binaries generated from the same version source code in different development machines?
I'll take that one. Yeah, I would definitely agree. As I mentioned, verifying the source of where this came from, making sure that you can see it, this binary comes from this commit, and you can see that commit. It is important that the particular binary that gets distributed, you can see came from a verified build server. so that you know that it is secure and that the hash that you see, when the binary was published is correct. There are obviously some changes from binary to binary, even when you compile the same thing over and over again, just because of, maybe some symbols are flipped or, moved around. However, you are exactly right. The actual code should be the same every single time, and you should be able to verify that.
Does the crypto in the binary model only include authentication or full encryption of the binary?
So the crypto, I'm assuming that this question is asking about verifying the new updating, when you're updating crypto, verifying the module coming in. And so in our case, the binary model of crypto we went for is for all the crypto that EDK2 uses. So this includes hashing and encrypting and PKS7 and X509 and a bunch of other functionality. It's a pretty large surface area. So it's if you wanted to verify a new binary, you would definitely have to use the binary model version of crypto if you were using that. Hopefully that answers the question.
I wanted to chime in and just say again on the size part. Keep in mind that DFCI and MFCI brought in more modules that perform crypto, and by using this binary model, we were able to have quite a bit of savings over having multiple copies of crypto carried in the flash.
What is the EDK2 build performance difference between PyTools versus the original base tools?
I would say that the worse, but let me couch that with so the ultimate build process is executed and handed off to base tools. What PyTools is really targeting is making that environment a little bit easier to configure. One of the things that we did really early on, and anybody who's been following sort of the Project Mu contributions is aware of this, we decided to investigate a submodule pattern. The idea that we're going to go through and we're going to cut up the entire platform source tree and figure out which sections are common to certain behaviors or to certain platforms or to certain requirements, and we're going to wrap those in their own repository. The borders of these repositories are not only dictated by technical requirements, but they more and more were informed by business requirements. These boundaries were boundaries where boundaries of collaboration. That's not. Nobody wants to call it a boundary of collaboration. Let's actually say they were designated pools of collaboration. Everybody likes a pool, but that more complicated, more hierarchical and stratified code layout necessitated solutions so that each platform didn't have to have massive amounts of configuration for exactly which repos it intends to use, not only which repos it intends to use, but carry a bunch of configuration for those repos as those repos see changes. So what ends up happening is you would like to treat the repo below you as more or less transparent when you choose to update. So an update should never be forced on you. You should be able to evaluate your code. But when you choose to update from one release to another, all you should really have to do is look at the change notes for any breaking changes and then update once you've acknowledged those breaking changes. In order to keep those breaking changes to a minimum, we needed a way to encapsulate some of the build configuration and some of the other things into each individual repo so that the configuration would change as the repo changed, or as the target branch or target release changed. All of this to say, we wrote tools around that so that we wouldn't have to, because even though Microsoft is a huge company, and even though a lot of this came out of Surface, and Surface is a huge department, our core team is a very small team, and we take on a bunch of different broad work, and we did not want to be contributing resources to doing this often. So those are the tools that we wrote for ourselves because we're very lazy, to enable us to support as many platforms and as many departments within Microsoft as possible. So it does run slower because in reality PyTools is a bunch of meta processing on top of base tools, but with the goal of enabling you to, one, only build what you have to build without having to go through and manage it as granularly as otherwise, but two, to give you that flexibility so that hopefully the man hours that you save, doing the configuration or become machine hours running builds on build servers somewhere, and hopefully it all balances out.
If I might comment, add to what Brett said, something that maybe we didn't state it outright, but it spans from Brett's intro on why we're committed to UEFI as a way to build a variety of devices, and PyTools, what is it for? Componentization. We work on large-scale projects that span teams, that span companies, right? Silicon providers, different silicon for, maybe CPU versus embedded controller versus audio versus video, and to that end, when we're trying to span across these teams and companies, componentization, right? Those interfaces are important. And then where this ties into PyTools is we build reusable components that PyTools makes it easier, we think, to integrate into different products. So again, does it build a little slower, but it gives us that componentization that ends up boosting our efficiency when we reuse these components across products, and when we service these components across products. So, thank you.
Are there any additional protections in the OS for PRM over what the OS already offers?
I think we're working on that. I think that is part of the goal, that not only is it a performance gain, but it is a security gain for the host OS. Where this gets tricky is finding the balance between, many of the people that have been involved for years will remember STM, and the fact that STM, is a great idea, but it didn't really get particularly far because of these questions around, do we want to require this level of designation? And at the time, we didn't. But that conversation is shifting. The realities of the security landscape are dictating that even though we wanted to avoid having to identify exactly what resources a handler would touch or exactly what memory ranges a handler would need access to, perhaps that is a reality, that even though it seemed like a nice to have, that perhaps it is in fact a requirement no matter what solution we end up with. So those security advantages are evolving. I would say that if that is an interest of yours, let's be part of the discussion early to see what targets we can hit with PRM versus what targets we need to hit with other protections. There are other solutions such as proprietary hardware solutions to monitor these things that look a lot closer to STM. There's lighter weight things that look more like kernels that work alongside the OS. There's hypervisor solutions. So they are coming. I don't have a ton of details. Frankly, the colleague that is developing this technology wasn't able to make this talk, or rather, we didn't want to overboard the talk, overload the talk with too many presenters. But he'd be better to answer the question. But I think if it's an interest series, get involved. Follow some of the links, ask questions on the platform, engage with us on the forums that we're discussing that.
If I might quickly build on what Brett said, I think where it is right now is that the security value or security benefit is that features that are currently implemented in SMM that do not really require a security boundary between kernel and firmware can be moved from SMM into, let's say, kernel or ring 0 type environment, thus really reducing the attack surface and unnecessary complexity from the SMM environment. So I think that's at least where we are now. If you have different perspectives on that, like Brett said, please engage. Thank you.
Does DSCI require access to the internet, or can it be run within a self-contained data center?
So the DSCI source code is open source. You can do with it as you like. It has a very permissive license. If you want to take it off the shelf and ask what first-class features does it have today, today it has a dependency on Microsoft services, and we do not offer sort of an offline configuration. So that's not a feature today. But if you want it, and there's a good business justification, anything can happen. Thank you.
Great. Well, that was actually our last audience question. The presenters have provided a few links here as well if you guys want to check those out after the webinar wraps up. But as a note for everybody on the line, the presentation slides will be available on the UEFI Forum website, and we'll be uploading this video to our UEFI Forum YouTube, as well as it will also be available on the Bright Talk channel. So thank you all so much for joining us.
Yeah, thank you.
Thanks, everyone.
And to address an anonymous question, yes, my photo was from the Dell BIOS lab, from the infamous Supercube, and I'd be lying if I said I didn't miss it. Sometimes.
Thank you.
Thanks, everyone.